Welcome to the second AGN Tourney. Today the knights are Margherita, Giustini, and Francesco Shankar, and the chair is Paola Marziani. So just have to tell you that the talks will be recorded, so we have the permission by the speakers, but of course anyone that will intervene will be recorded, so you should know that. And well, just remember to mute your microphone and switch off your camera. And so, Paola, it's up to you. Thanks.
Well, it is a pleasure to welcome and to introduce the speakers of today, Margherita, Giustini, and of course, Francesco Shankar. Margherita obtained her PhD in astronomy. Well, Paolo, maybe you can mute. There is some background noise that is really disturbing. Let me start over again. Margherita Giustini obtained her PhD in astronomy at the University of Bologna with a thesis on accretion disk wind in AGN, an X-ray view. And after a postdoctoral experience in the USA at the University of Maryland and with the European Space Agency, she still works as a postdoctoral researcher at the Centro, the Astrobiologia of the European Space Agency in Madrid. And presently, she's the leader of a research project focused on unveiling supermassive black hole winds from space. And let me say that she has made important contribution in the understanding of the physics of accretion disk wind in AGN using UV and X-ray observation, specifically in connecting the winds to the accretion properties of the black hole, like mass and accretion rate. Francesco obtained his PhD at CSIC and afterward was awarded a postdoctoral position at Ohio State University at the Max Planck Institute for Astrophysics and then at the Osservatorio de Paris. Afterward, he joined the Department of Physics and Astronomy at the University of Southampton in 2013. Let me say that he has studied black hole demography using the continuity equation in a cosmological context, coevolution of galaxies and AGN, and pioneered an original approach based on semi-empirical and analytical modeling. Okay, let me say that given the breadth of today's subject, the speaker have decided to focus mainly on evolution and triggering on one side and on the orientation on the other side. Before giving the floor to the speaker, let me remind to mute your mics and turn off the cameras. I still can hear some background noise, I don't know from where. And let me repeat, as Paolo said, that the talk will be recorded. Please write. Or signal your intention to ask a question in the chat. So please, Margherita, if you want to start with your presentation.
Yes. Can you hear me well?
Yes.
Great.
Yes.
So I will start. So thank you very much, Paola. So I will focus mainly on AGN orientation and obscuration during this talk. So the question that we would like to answer is how do radiation pressure driven these winds can fit into the geometrical and evolutionary schemes of AGN. And in the more than a half of my talk will be devoted to try to explain this plot. So this plot is taken from an article of last year that I wrote with Daniel. I think that the bottom part of the presentation is obscured, but anyway, let's go ahead. So what we do? We consider radiation, the effect of radiation into the gaseous inner environment of AGN. We know that AGN are very luminous, so radiation pressure probably plays a role into shaping the inner environment of these objects. Now, by definition, radiation pressure is able to push strong winds once we overcome the so-called Eddington limit. And the amount of luminosity in terms of Eddington limit is usually called the Eddington ratio. And during the remainder of this talk, I will mostly call it m dot for short. So when your m dot is above 1, the radiation pressure overcomes the gravity pull and an outflow of matter is launched. But usually the classical Eddington limit is computed for a spherically symmetric matter and especially fully ionized matter. And so what we use is the Thomson cross-section. What happens in reality is that when matter is only partially ionized, things get much more complicated, but also much more interesting. And specifically, the effective cross-section for the interaction of radiation with matter is much, much larger in the case of partially ionized matter, easily by factor of tens of hundreds, up to thousands compared to the pure electroscattering. And what does this mean? This means that even when you are below the nominal Eddington limit by factor of tens or hundreds or even thousands, you can still be able to launch very powerful winds from the inner regions of AGN. Now, the effective cross-section for the interaction of radiation and matter is very large, especially in the presence of very closely spaced spectral transitions. And this happens especially in the ultraviolet band. So we know that in the ultraviolet, we have a plethora, a lot of spectral transitions which are very close in wavelength space one to each other. And this makes the effective cross-section for radiation pressure to be very, very large. This plot is taken from Dunn et al. 2019, and here is plotted with the thick black line on top is the so-called force multiplier, is a factor that tells you how much above you are compared to electroscattering when you're dealing with partially ionized matter. And so you can see that in the ultraviolet regime, which is on the left in this plot, you are always well above the one level. So you're always well above the electron scattering contribution. In the X-ray band, you also can be well above the electron scattering contribution, but you're always well below the contribution in the ultraviolet. And this is mainly because we have very few spectral transition in the X-ray band compared to the ultraviolet band. So when radiation pressure acts on spectral lines to push matter, we usually talk about line driving. So when we speak about UV or X-ray line driving, meaning X-ray or UV photons able to push on spectral lines and then drive matter outflows. Now, in AGN, most of the spectral energy distribution in luminous AGN, at least the peak of the spectral energy distribution happens in the ultraviolet band. So ultraviolet line driving should be important in AGN. On the contrary, X-ray line driving, while can be still important to launch some wind, especially in the iron K band, in the case of AGN, mostly concurs to destroy the wind. And why? Because X-ray photons have much more energy than the atoms which retains UV spectral transition. So the ionizing flux of X-rays tends to over-ionize these UV atoms, UV absorbing atoms. And when the electrons are stripped, the electron cross-section again becomes very small. And so the strength of the wind becomes weaker. So in AGN, we can say that in the radiation pressure, this wind scenario, what is critical is the UV to X-ray flux ratio, meaning that when this ratio is very large, so in the case, for example, of X-ray weak AGN, we can expect very strong radiation pressure-driven disk winds. On the contrary, when the X-ray flux is very large compared to the UV one, we do not expect such strong winds to be present. So what we ask ourselves is, given that the spectral energy distribution of AGN changes with different properties of AGN, specifically m dot and black hole mass, how will the accretion disk wind change accordingly? And we came up with a simple scenario where we focus on the inner parsec of AGN. So we make use of basically ultraviolet and X-ray observation, and we restrict ourselves to the case of stationary accretion. So we consider m dot to be constant in each case of AGN, or if varying, it's varying extremely slowly. So its variation can be considered negligible. And we came up with 5 different regimes where we can divide the different appearance of AGN given their different m dot. So the ingredients of our scheme are the following. This is a side view of an AGN. So at the center you have the black hole. The scale is logarithmic, so we are observing again more or less the central inner parsec of an AGN. And around the black hole, we paint the accretion flow that we divide in optically thin matter in green, in pink, sorry, and optically thick matter in green. And then the ejection flow that we represent with arrows, which are representation of the streamlines of the flow. And the thickness and the length of these arrows are proportional to the strength of the wind in terms of column density entrained and in terms of terminal velocity. And the duty cycle is also represented in this plot, meaning that continuous streamlines represent persistent flows of matter, while dashed and dotted lines represent flows of matter which have lower and lower duty cycles. So this is more or less the basic sketch. So this could be, for example, a Seyfert galaxy. But let's see each one of the small regimes of m dot, how would an AGN behave, or a galactic nucleo in this case. Let's start at very low m dot. So when the black hole is basically not eating, so it's not accreting, so we are observing quiescent nuclei. This could be, for example, the case of our own galactic center, Sagittarius A star. In this case, the accretion flow is geometrically thick and optically thin. So thermal emission is absent. There is no line-driven disk winds, basically because there is no disk, and there is also no UV radiation. And the spectral energy distribution, which is plotted on the right, focusing on the UV to the soft X-ray band, is dominated by non-thermal emission, mainly due to the emission from the jet, so synchrotron from the jet, and Compton emission from the hot accretion flow. Winds can be present, yes, they can be present, but they will be very, very slow, with velocities up to, at most, a few hundreds kilometers per second, and these winds will be driven by either magnetic forces or thermal pressure, but not by radiation. When we increase m dot, so we start making the system accreting a bit more, what happens is that matter starts to collapse from the outer regions, starts to collapse, so starts to become geometrically thin, and more optically thick. So from the outer regions, the system starts to emit thermally. And in the spectral energy distribution, you can start observing some non-negligible contribution from the thermal, let's say, outer portions of an accretion disk, or thermal component anyway. But again, this will happen at very large radii. So if winds are present, again, like in the previous case, they will be mainly thermally or magnetically driven winds, because there are basically not enough UV photons to push any kind of powerful mass outflow from these systems with radiation. Then we enter into the interesting regime, speaking of luminous AGN, when we are above more or less 100 of the Eddington ratio. We enter into the optically thick regime. So in this case, an AGN will resemble the picture that we have, more or less classical picture that we have in mind, with a disk, with a geometrically thin and optically thick accretion disk, which extend very close to the central black hole. In the center, there will be the distribution of optically thin matter, that in this case we call the X-ray corona, which will Compton upscatter the UV photons of the disk, and will give an X-ray power law component into the spectral energy distribution of the system. In this case, because the disk is formed and because there are plenty of UV photons, it is possible to launch powerful radiation-driven accretion disk winds. However, the strength of this wind in this case will depend strongly on the black hole mass. Now, we know that the temperature of the accretion disk around black holes is inversely proportional to the mass of the black hole itself. So in the case of very large black hole, the disk will be colder. And in the case of very small black holes, the disk will be much hotter. So delivering much more X-rays, which try to destroy the wind. So we separate this regime into two classes of black hole mass. So very small black hole masses, let's say 10 to the 6 solar masses or so, in the top row, when the disk is quite hot. And so a strong wind cannot be formed, especially close to the black hole, because close to the black hole, you are dominated by X-rays from the optically thin matter. And so the wind is failed. And in this plot, we draw with little blue wiggles this failed wind, which is basically material which receives a lot of push from radiation, but not enough to leave the system. And so falls back toward the disk plane and has some kind of a chaotic behavior, dynamical behavior, and it's a failed wind. And if you compare the first row with the second row, where the black hole mass is much larger, in this case, the accretion disk will be colder, and the wind can be launched from closer in to the black hole. And so this wind, in the second case, will also reach much larger terminal velocities. Then what happens if we increase even more the m dot? We enter into the quasar regime, what we call the quasar regime. So here, yes, you are dominated by the accretion disk, which stands very close to the black hole, possibly up to the innermost stable circular orbit. The X-ray corona is very small, geometrically speaking, but especially energetically speaking, meaning that these quasars are X-ray weak. So the contribution of the X-ray power compared to the optical UV accretion disk is low. And these are the most favorable conditions for radiation-driven accretion disk winds to exist. Again, in this case, the black hole mass will play a significant role in this scheme. So only for the largest black hole mass, the disk will be cold enough to prevent over-ionization from X-rays and so to launch very powerful winds. Another way to see this is that for lower black hole masses, the duty cycle, the covering factor of the wind will be much smaller, while for larger black hole mass, the disk will be colder and the covering factor of the wind will be larger. When you go eventually above Eddington, the covering factor of this wind will be maximum. So when you are super-Eddington, the inner portion of the disk of the accretion flow puffs up because the radiation pressure is too high to support geometrically thin distribution of matter. And you have powerful outflows launched by radiation, both in the polar regions and in the equatorial region. So you can imagine like almost a 4 pi outflow. So this is the general scheme. So putting all together these 5 different regimes, again, m dot is increasing from the top to the bottom. And in the case of quiescent low luminosity AGN and super-Eddington AGN, the geometry is not very important, meaning that these objects are more or less isotropic except for the polar regions, so except for a very small opening angle. While when you enter into the Seifert quasar regime, geometrical effects are very important within this scenario. So back to the plot of the beginning, let's take, for example, a highly accreting AGN, but with a very small black hole mass, let's say a few 10 to the 6 solar masses. This will be the case of the narrow line Seifert ones, for example. So here I plot 4 different names of famous AGN, which depending on the line of sight, will give different spectral characteristics, both in the UV and in the X-rays. So for example, in the polar region will be the only case where you will have like an obstructed view of the central engine. While moving your line of sight toward the equatorial region, you will start increasing the probability to intercept the wind along your line of sight. What happens if we decrease a little bit the Eddington ratio of this system? We will get a broad line Seifert one, meaning in this case, the relative contribution of the X-rays to the UV is much larger. So this AGN will be more dominated by X-rays, so their winds will be weaker compared to the winds of narrow line Seifert ones. What happens if we increase the black hole mass of this system? We get what we call mini broad absorption line quasars. So quasars where winds are present, but they're not that strong as in the classical bulk quasars. In this case, it will be very difficult to distinguish mini bulk quasars regime from the narrow line Seyfert-1 regime, for example. So if you see, the winds are quite similar. What will be very easy to distinguish will be the most extreme case. So when you go at large black hole masses and large Eddington ratios, you will enter the quasar regime, so the broad absorption line quasar regime, which means that for many inclination of your line of sight, you will be able to intercept very powerful winds with very large terminal velocities and very large column densities entrained into the flow. So this is the view that we had about this stationary accretion on AGN. So if we put into a plane of m dot versus black hole mass the different AGN that we studied, we can identify 4 physically different regimes of wind. So there will be a region where there is no wind, radiation-driven wind at all. There will be a region, the region of the classical Seyfert galaxies, where you are dominated by a failed wind, so a successful wind cannot be launched, the yellow region in this plot. And then you will enter the region at large Eddington ratio and black hole mass where strong winds can be launched. And what happens to an AGN? What happens is that during its life, an AGN could also occupy different areas of this plot, of this plane. For example, by increasing its black hole mass, and so decreasing the temperature of this disk, or for example, by changing its mass accretion rate. But the conclusion of this work was that definitely in both orientation and evolution are important in the case of radiation-driven accretion disk winds in AGN. And so we should consider both factors. And we were quite happy with this scenario, so we were thinking, okay, we kind of see the light somehow, but no. So in the rest of my talk, I would like to present you some recent results that made us realize that we were really dealing with stationary accretion. We were really dealing with a very easy situation because reality is more complicated. So the rest of the slides will have a dark background because we are really going into the darkness here. So, yeah, almost 2 years ago, XMM Newton delivered one of the most surprising observations that I've seen. During one orbit, especially one orbit in January 2019, this is what XMM Newton observed. So this is a true X-ray image taken with the EPIC PN. And in the bottom, you can see a representation of the X-ray light curve. And the total duration of the light curve of the observation is one full orbit of XMM Newton. So it's more or less 36 hours. And this source flares in an extremely regular way. So it flares every about 9 hours. These flares are extremely sharp. So each one lasts about 1 hour. And they are very intense. So the intensity of this flare can be up to 2 orders of magnitude, the count rate that compared to the quiescent level. So this was a big surprise. And what was this color? What was this source? So the name of this source is GSN 069. It was a very not famous source until 2 years ago, until 10 years ago, more or less, when XMM Newton suddenly observed an increase in its X-ray flux by a factor of more 200 compared to ROSAT archival observation. And so telescopes started to observe it and to monitor it. On the bottom panel, you can see, bottom right panel, you can see the X-ray light curve during 10 years. And the decay in flux is consistent with a tidal disruption event, a very long-lived tidal disruption event. So the idea is that sometimes between 1994 ROSAT observation and 2010, this source disrupted a red giant star, and so got activated. Now, during the long pointings made it with XMM Newton and Chandra in 2018 and 19, this new phenomenon was discovered. So this is a collection of the light curves of the source collected from 2010 up to 2019. And you can see that in 2010, the source was behaving like any AGN, like in an erratic way. In 2014, the light curve was quite strange, meaning that it was very flat to be a typical small black hole AGN. But then in 2018 onward, the light curves displayed something never observed before. So we decided to call this new cosmic signal quasi-periodic eruption, QPE, mainly to distinguish them from QPOs, from quasi-periodic oscillations, which are often observed in X-ray binaries and sometimes in AGN as well now, but which are way more gentler, and they do not resemble these very sharp, very intense spikes. So what are QPs? QPs are oscillations of the very inner accretion flow between a very cold phase and a warmer phase. So GSN 069...
Including 2 minutes.
Yes, thank you. It's an AGN which doesn't have X-ray corona, so it only has a disk emission. And during the QP, the temperature of this accretion flow smoothly and rapidly increases up to about 120 electron volts and then comes back to the value before the QP. A possible interpretation, it could be that after the activation of this AGN, the remnant of the red giant star started to orbit the black hole, and every 9 hours interact with something which is close to the black hole and gives these very bright spikes of emission. This is an hypothesis. Is this object unique? No, it's not unique. So we identified QPs in a second AGN, RSJ 1301.9, and this is an AGN which shared many characteristics with GSN 069, mainly small black hole mass and the absence of an X-ray corona and interesting X-ray variability. And indeed, a 2009 observation with XMM showed the presence of 3 very strong QPs in its light curves. And also an archival observation confirmed the presence of this phenomenon since at least 20 years. But as you can see, the separation between these QPs in the second galaxy is not as regular as in the discovery object. So what we did is we went asking for a longer observation with XMM Newton, which was performed 3 months ago. And this is the results that we got. So this is, again, this is a movie. This is an epic PN image. Each second of image corresponds to 1 hour of exposure. So this is, again, a 36 hours long observation. And we observe spikes of emission, so again, QPs, but spaced not as regularly as we were expecting. So if you want to transform these graphical results into a light curve, this is what we observed. So in 36 hours, we observed 9.5 events, and the time separation between them is completely different among each couple of them. So there is no immediate pattern of variability easily identifiable in these light curves. Perhaps we are observing multiple patterns of variability. We don't know, big enigma. Another AGN, very quickly, that caught our attention was 1AS 1927. In this work by Ricci et al. 2020, this AGN, which went through, again, a tidal disruption event in the optical, this AGN displayed this crazy variability in the X-rays. So in the left, you can see the light curve. And in the right, you can see corresponding spectra in the X-rays. And to make the story short, what happened, according to the author, so the likely possibility is like the tidal disruption event, the optical one destroyed, so destabilized the accretion disk, the inner accretion flow, the inner accretion disk, and destroyed, this destabilization destroyed the inner X-ray corona. The corona then had time to reform, and reform in, even though weaker than before, but just in a few weeks. So to conclude, orientation and evolution, they count? Yes, they both count in AGN. Can we understand the AGN geometry and evolution by inserting an accretion disk wind? Yes, in the case of stationary accretion, but reality is much more complicated. So it appears that accretion in these low redshift sources is not stationary, and so dramatic spectral changes are happening, and let's see, the room for understanding is still wide open, and I stop here.
Margherita for this insightful presentation, and we give the floor to Francesco for his talk.
Okay, thank you. Can you see it?
Yes.
Okay, very good. So first of all, I would like to join Margherita in thanking the organizers for giving us this opportunity. Thank you very much. It's really interesting setting, and we are enjoying it a lot. So I'm going to follow on Margherita's path, and I'm going to discuss evolution versus orientation. Now, Margherita has discussed in detail the orientation models, which are on the right-hand side of this slide. I'm going to mostly, I'll be highly complementary to what Margherita showed, and I'm going to discuss mostly evolutionary models on the left-hand side, where you go through different phases of, during accretion of the black hole, you go through different phases of the host, and this appears at different wavelengths. Now, my approach will be complementary in a number of ways. I'm not going to discuss single sources, but I'm going to present a population analysis of AGN. I'm going from low redshift to high redshifts as well. Most, in fact, of my talk will be mostly at high redshift. And I'm going to go from observation to a more theoretically oriented approach. So it's highly complementary in both the content, but also the methodology, but still it's within the evolution versus orientation topic. So when we talk about evolution, I think this is one of the first plots that we have in mind from a review from Alexander and Hickox, and has been this idea has been around for decades. Has been pushed forward by a number of theoretical groups and observational groups, in fact, all over the world. So let me just, so that we all start from the same page, let me give you just an overview of this. So there is some triggering happening in stage 1, whatever that triggering is. Let me call it for now a gas-rich merger, but it can be just, you know, a galaxy that is forming. And then this goes through a phase 2 in which it goes dust enshrouded. It's a sub-millimeter galaxy, ultra-luminous infrared galaxy. And here you start showing a black hole, a seed black hole that starts growing and shining, possibly in the X-rays. And there we have a stage in which it becomes obscured quasar, and then eventually an obscured quasar, an optical quasar, the way we would call it, define usually. And then eventually down the line, it will the descendant will be an early type galaxy. Now, of course, the AGN light curve, the AGN growth will mostly happen within stages 2, 3, and 4. So these stages are quite short with respect to the rest of the phases from 1 to 5 that can happen on billions of years. But the phases 2 and 3, 4 could be quite fast in forming both the black hole and also the AGN, the black hole, and also the host galaxy. So this is just to give you an overview. And so most of the theoreticians that work in this field, they start the building block of their models is the AGN light curve. And here we basically show the same trends that were showing in the previous cartoon. So there is a triggering phase. There is a seed that starts rising very fast. It grows both in luminosity, in accretion rate, and black hole mass. So in this phase, the Eddington ratios are most constant. It reaches a certain peak, and then it falls off. It shuts down after that. The shutdown is most probably induced by, in different models, can be induced because there is quasar feedback. There is also a lot of gas that is being used via star formation. So there is a combination of all these processes. Eventually, this process shuts down. And this type of light curve is present in all types of models that are out there. These can be semi-empirical models, they can be semi-analytic models, numerical models. They will all show you the same type of pattern. So let me show you, for example, a couple of two recent experiments in this respect. So on the left-hand side, this is a nice paper by Fabio Fontanot, just published this year. And Fabio experimented with different type of accretion rates on the black hole. and you can see that there is this light curve. This is the accretion rate. You can see that there is a peak, there is an increasing phase, and then a very long phase after the peak, post-peak phase. This is on the right-hand side. You can see this is a light curve that comes from a continuity equation approach. This is a nice paper from Aversa, Lapie, and collaborators. In this respect, this is slightly different from a semi-analytic model, because this is a phenomenological model in which you input the light curve of an AGN, and you process this through a continuity equation that matches at each epoch the luminosity function of AGN. So, but the bottom line is that this light curve is very similar in all of these models. There is a fast growth, there is a peak, and there is a descending phase. So now you can convolve this light curve with the number of episodes in which you start triggering black holes. So, for example, you can convolve this light curve with the number of mergers from dark matter halos, for example. This is an exercise that was already proposed 20 years back by Whitey and Loeb. And you can try and do this, and you will see that you will be able to go very far in producing a number of observables. I will show you this in the next slide. Let me just specify one thing here, is that all of these models tend to rely on some common features that are usually you need to start with massive seeds, and or you need to have some sort of super-Eddington accretion in the very initial stages, especially here and especially at high redshifts. The reason being is that you want to create enough luminous quasars fast enough to be able to fit the bolometric quasar luminosity function at high redshifts, which is a challenge. And you do need this type of common features if you want to try and reproduce those type of data. So this is an exercise that I pursued some years ago, but basically just to give you an idea of how these models work. And so you, as I said, you get that luminosity, that light curve, you convolve it with some rates for the merger rates, for example, of dark matter halos, or formation rates of halos, or some triggering mechanisms, minor mergers, and so on. You can convolve this, and you come up with some luminosity functions. These are the solid lines. These are the prediction of this model. And these are data on the bolometric luminosity function. And more or less, these models do tend to reproduce the bulk of the data. So they are reasonably successful in matching the data with relatively easiness. You don't need to struggle too much to be able to reproduce these data. And from this type of light curves, then you can extract also the Eddington ratio distributions. So from the luminosity that I showed you before, because you have luminosity, you have black hole mass, and you have the time spent by the black hole mass at each luminosity, you can extract what is the probability that a given black hole spends at a given Eddington ratio. So you can directly translate those light curves in Eddington ratio distributions. And this exercise is shown here in this plot. This is at fixed black hole mass at different redshifts. And you can see that the same light curves that I showed you before that roughly match the AGN bolometric luminosity functions translate into Eddington ratio distribution that look like this. So there are kind of Gaussian distributions at high redshifts, and then they become broader and broader when you go to lower redshifts, and they tend to approach this sort of Schechter-like distribution. And if you just focus on redshift 1, for example, just to give you an idea, different black hole masses, you do see that all these Eddington ratio distributions are all alike for different black hole mass, underlying black hole masses. And they all follow this type of Schechter function below redshift 2 or so. And this is quite intriguing because if you look at the data do suggest the same trends. So this is a paper by James Ayard. The same group published other papers more recently showing similar results from different larger data sets. And you can see here that there is again this type of power law and a little bit of a year of fall off at the higher Eddingtons, which recalls this type of Schechter function that you see over here. And this is not the only group. Of course, Others have done this. Angela Bongiorno and Andrea Merloni have published this type of papers on the Eddington ratio distributions. And you can see that basically you always find the same trends. So there is a power law and a sort of a fall off at high luminosity, high Eddington ratios. So so it seems that, you know, at least at face value, these relatively straightforward models can reproduce a number of observables. But of course, no model is perfect, and there are serious shortcomings, and this is something that I want to highlight in this contribution of mine in the context of the evolutionary models. So when we talk about these evolutionary models in a multi-wavelength fashion, what theorists and observers have put forward as an hypothesis, working hypothesis, is that before the peak, there is a lot of star formation, there is a lot of dust, and definitely there is, most probably, the galaxy will appear dust obscured. And if you want to probe the AGN, you cannot really do it in the optical, you have to go to the X-rays. If you want to try and get the first stages of evolution of this AGN. And then eventually, the dust will be cleared, the gas will be consumed, and the quasar will shine in the optical phase. And so here you could, so you can play around with the statistics here. So starting from the same luminosity function, you can break down the luminosity function into pieces and say this light curve into pieces, and say, you know, before the peak, there is all the accretions that happens before the peak is obscured and will be recorded in the obscured AGN, while whatever happens around the peak will be recorded in the optical luminosity function. And so you can work around with this type of tricks and try to see if you're actually able to reproduce the multi-wavelength AGN luminosity at different epochs. So here is again another exercise that we tried with Andrea Lapi several years back now. And this is the optical luminosity function in the B band, all these data. And these curves show you the conversion from total luminosity function to a luminosity function that is unobscured, in the sense that I showed you here. It becomes unobscured only around the peak. Now, we were able to go from the total to an optical luminosity function. So a luminosity function that was, with the same model, we were able to match both quantities if and only if this shutdown phase was contained, was not too prolonged, too long. And the reason being that if this phase is too long, you have too many faint AGN that pile up in your optical luminosity function. And this tends to spoil the match with the faint end of the optical luminosity function. So there is a very intriguing and interesting compromise that you need to play, especially at high redshift. This is sensitive to the exact shape of the light curve. But there are also other issues. For example, this is a paper put forward a few years back by Giulia Rodiguero. And she also highlighted that there is some tensions with the data when you look at these light curves and for example, data derived from far infrared. And you can see over here that these color bars are the data both during the main sequence of the main sequence. And what they claim in this paper is basically that you're never able to reproduce this type of steep increase in the X-rays, in the X-ray luminosities when you go beyond a certain epoch. While the models would suggest, the models are these solid lines over here, would suggest a steep rise in the light curves, they don't actually really see it in their data. So I'm just showing you here a number of possible tensions, and just to foster discussion, of course, in the spirit of this of these talks. Again, let me show you another point of possible tension here. This is the bias. So this is the clustering. So this is large-scale bias as a function of bolometric luminosity, and this is a redshift 4. This has data from Shen, U-Shen, a redshift 4 from quasars from Sloan. And what I'm showing you here are the predictions from the same models that I showed you before with the same light curves. And you can see here, this model over here, this dot dash line over here at the bottom, is a model in which I have increased the delay between the triggering and the peak phase. And if you and what I've done is that I've allowed for a broader luminosity light curve at high redshifts. And you can see that if you do that, your clustering strength drops. There are two reasons for this. The clustering strength drops because you are increasing your light curve, so you are increasing the distribution of Eddington ratios, and therefore the clustering strength drops because basically the scatter is increasing. And also because there is a sort of underlying passive bias, because if you wait too long since the triggering to shine your AGN, then the clustering at high redshift has dropped due to passive evolution. So there are a number of effects that enter into this calculation, and that shows you that, again, the clustering could be a signal to be able to constrain the light curves of AGN, especially at high redshift. So the take-home message, my first take-home message is that evolutionary models are more or less good, but we need to pay attention to a number of observables, like the multi-wavelength luminosity function, star formation rates, and the clustering of AGN. Now, let me show you another couple of things. Of course, there is a peak over here, and this peak could resemble the so-called quasar mode feedback. So this is the quasar mode feedback. So you could assume that at the peak, the black hole reaches its close to maximum mass, and this peak is reached when basically the energy released by the quasar is consistent with the potential well of the system, is at the same rate of the potential well of the system. So this is a back of the envelope calculation that puts in numbers what I just described to you in words. So basically you release some amount of energy in a dynamical time, and if this is comparable or even larger than the potential well of the system, this naturally should imply an m sigma relation of the order of 10 to the sigma to the 5th, or possibly sigma to the 4th if you consider conservation of momentum. Of course, this is just a back of the envelope calculations. Reality is much harder than that. If you really want to model AGN feedback, it's much more convolved. There are a number of processes that you need to take into account. Here I'm just mentioning one of these latest calculations by Nicola Menci that takes into account the full evolution of the blast wave in disk systems, but I don't have the time to go through this. So these light curves, but what we can learn from these light curves, from these simple models, is does the M black hole sigma actually is consistent with the is the M black hole sigma that you extract from these light curve models consistent with the data? So let me skip these two and let me show you the result. The answer is yes. So the M sigma is consistent with, if you actually use that peak function, that is the same peak function that is able to match the bolometric luminosity function at large luminosity and large redshifts. The same light curve is able to reproduce an M sigma relation using this quasar mode feedback that is roughly consistent with the data. So let me just show you one panel of these four, because the story is the same. So we can focus, for example, redshift 4. This solid line is the M sigma that you would predict from those models at the peak, and this gray band are local data, and these symbols over here is what you would extract when in the final black hole. So these simple models are roughly consistent with a M sigma relation as you would observe in the local universe, and also they would predict as a very weak evolution in the M sigma relation. So again, this is I would say it's a kind of a success of the model, or another way to look at the models at least. However, these models fail in reproducing the residuals in the scaling relations. So if you really want to look at the details of how well they reproduce the scaling relations, you can see, and this is a paper that we published a few years back with Enrico Barause, these models that are based on quasar mode feedback, at least on thermal feedback, they fail in reproducing the residuals in the scaling relations, which is quite important because we have a number of data sets now that we can compare with, and it's not encouraging that these models fail in this respect. So the take-home message from this part is just I wanted to say that velocity dispersion, which is a fundamental property of these models, is a fundamental variable. And but you should pay attention when you compare with the scaling relations also to residuals, because this is a very fundamental property of these scaling relations. And now we have the data to actually study this in detail. I just want to highlight in my last slides that, of course,
conclude in 2 minutes.
Yeah. Okay. Thank you. So I'll conclude in 2 minutes. I just want to show you a couple of two slides that these models are not comprehensive. Of course, they fail badly in reproducing the full luminosity function of AGN. Mergers by themselves, we know that they're not enough. Michaela will discuss possibly more about this in her talk later on during the week. So do we have signs that show us that possibly mergers are not enough? Well, yes, we do. And I just want to show you a couple of these plots. Here we have this. These are another way to probe the triggering of AGN, which are not necessarily merger based. So if you look at AGN satellites on the top panel, and if you look at AGN clustering in the bottom panel, you do see that the data, these are the pink regions are the data, these are data from Paul Martini and Laura Penterici. They suggest that the fraction of satellites in groups and clusters is very large. And in groups and clusters, you don't expect mergers to play any role at all. And in fact, this solid line over here, this blue line, is a model in which includes disk instabilities within, so in situ triggering for this AGN. And possibly these are the type of data we should look at in order to probe different ways to trigger AGN. And also another way to trigger AGN could be, another way to probe the triggering of AGN could be in this bottom panel over here by looking at the small scale clustering of AGN. And you can see here, these are different models with different Q parameters. This Q parameter parameterizes the relative probability for centrals and for satellites and centrals to be active. So the larger this Q parameter, the larger the probability of satellites to be active. And you can see that if you want to reproduce the small scale clustering of this AGN, you need to have a high probability for satellite AGN to be active. So I want to conclude here. I don't have more to add. I'll just leave you with my conclusion, and that's it. I don't want to discuss more.
Francesco, for your talk, and I think that we can consider the question. The first question comes from Maurizio. Paulillo, it's a question for Margherita. Please, Maurizio.
I was wondering if the dynamical, thermal, and other time scales in the disk and in the AGN are consistent with the time scale of the pulsation that you see for QPs.
Okay. Okay. So disk instabilities was probably the first hypothesis that we thought about, and so the answer is yes and no. So let's say QPs, the time separation between QPs is very short. So in GSM 069 is about 9 hours. And the QPs last about 1 hour. Now, the black hole mass in GSM 069 is quite small. So it's estimated to be 400,000 solar masses, 4 times 10 to the 5. And for this AGN, we were able to compute numbers. So let's say if we make match the numbers that we have with the dynamical time scale, for example, or the viscous time scale for propagation of instabilities, we get that the viscous parameters alpha for disk instability must be very large, so well above 20%, for example, while it's typically hundreds, so it should be very large. Second, the scale height of the accretion flow should be quite large as well, so it should be around, I think, 20–30% in quiescence and about 1 during the QPs. So yes, dynamical timescales could be compatible with the QPs only if we are observing the very inner accretion flow, meaning a few gravitational radii really. And the other part of the story is that the accretion disk is not flaring during the QPs, so we don't observe variability in the UV. So it probably is not a disk instability in the traditional sense. And then in the second AGN, RxJ1302, things get more complicated because the black hole mass is larger than GSN 069, but the time scales that we observe are shorter. And so this goes in the other direction that we would expect. And so in this scenario, the viscosity parameter and the scale height should be even larger than in GSN 069. And I don't know how this would fit, but we are working hard to try to understand things.
It's a question from Boshina Czerny, and please, Boshina.
Since you have all those powerful winds, and those winds in a sense can play a role of the broadline region, and in particular also of the dust molecular torus. And if this dusty molecular torus then is really identified with powerful winds, as it was suggested by a number of people, then the covering factor of this dusty torus or wind, because of the radiation pressure, is universally always 45 degrees. This is what you see in simulations of Daniel Proga, right? Because your wind goes up and then it has to bend radially at when height is comparable to the radius. So my question is, observationally, this would look like a universal opening angle of the torus, not necessarily the covering factor in the sense of the optical depth, but in the sense of opening angle, yes. Do you think it's reasonable or not likely?
Okay, reasonable. Yes, I mean everything is reasonable in principle. What we did in this scenario. So let me say, what I think is going on is that on large scale, so on torus scale, which we don't go studying in our work, but on torus scale, probably you have, yes, radiation pressure acting on dust. So like you have shown in many words, so you can have a failed wind, failed dusty wind, producing the low ionization broadline region. So the same analogy, but pushing the flow closer to the black hole, we would have a radiation-driven disk wind and its failed component that would give the high ionization portion of the broadline region. So we would have high ionization broadline region driven by radiation pressure, so that should follow the scanning radiation, and the outer dusty wind, the outer wind driven by continuum pressure but on dust, that will also have a much larger radiation cross-section than electron scattering, of course. Does that answer the question?
Well, then observationally, this opening angle should be more or less universal, right? This is the main difference between the magnetically driven wind and radiation pressure driven wind. In the magnetically driven wind, you can have any opening angle, or actually you have outflow everywhere. In radiation pressure driven outflow, you have this empty 45-degree cone, more or less.
Yes.
Do we have it, or you are not sure?
No, I'm not sure about the observational evidences. Because that's the main reason why I try to focus on sub-parsec scale, because I'm really made use of UV and X-ray observations. So we don't really probe larger scales. So we decided just to keep it as easy as possible and just focus on the, let's say, few thousand gravitational radii. So we're speaking about the very inner accretion flow. So no, I'm sorry, I don't have any strong observational evidence for universal relationship of dusty torus problems. Yes.
Okay. Thank you.
Sure.
From Fabrizio Nicastro. Please, Fabrizio. Rita.
Okay. Here I am. I have a question for Margherita. The first is very simple. I didn't. You had a plot in which you had the accretion disk with a physical scale, distance, and on the other side there was the velocities of the terminal velocities of the outflow. What is the starting velocity that you assume to get those terminal velocities? Is the wind launch at what velocity probably?
No, it's just comparing the terminal velocity, the local escape velocity. So we just say this thing possible. So the closer you are to the black hole launching the wind, the faster is the terminal velocity.
So the launching velocity is the escape velocity at the
sorry?
So the velocity with which you launch the disk, the wind, is the escape velocity from at that distance.
Yes, it's just slightly larger than the escape velocity at the distance, and then the terminal velocity is about 3 times the local escape velocity.
Okay, then I have another question, which is well, it's more a comment than a question. I think when you separate UV and X-rays, what you really mean is actually low ionization and high ionization, because a wind which is high ionized doesn't have opacity in the UV, but actually it also doesn't have opacity in the soft X-rays, because there are plenty of transitions, special transitions from low ionization atoms in the X-rays. So the main difference between the Fox multiplier in the UV, in the X-rays, and is actually versus ionization parameter. You have a low ionization parameter, you have a very strong multiplier because you have transitions both in the and in the X-rays. When the ionization parameter is high, you only have transitions of very few highly ionized atoms in the X-rays. That is the main difference. But the reason I'm saying this is that you can still have a wind which is farther away from the central source, and the X-rays is still contributing a lot to lower ionization winds starting farther away. The contribution of X will still be very important.
Okay, yes.
So yeah, but what I'm saying this is, I don't think in that case fit very well with the different alpha X you have, because it doesn't really matter. It doesn't.
Yes, you're probably right. You're right here. Not probably. You're right here. I was probably related to. I probably left that alpha X into the presentation. I was writing it very, very quickly. So probably alpha OX. That's a good point. Should not have been there. So you spotted. Yes, a good point. Yes.
Well, the next question is still for Margherita from Alfredo Luminari. Please, Alfredo.
Hi, Margherita, and thank you for the presentation, both your one and one from Francesco. I just have a couple of halfway between question and comments for Margherita. The first one is about the mechanism with which you launch the wind, because you focus mainly on line driving, let's say, acceleration. But if I'm not missing something, you implicitly assume that there is always gas which is ready to be launched as a wind, independently from the configuration. So probably instead there might be some physical condition which can act like to facilitate or to reduce this amount of gas. And this is the first point, but obviously it's not easy to like make this more to detail this idea. And second one is for what concern X-ray radiation, because in line driving usually, or in radiation driving in generally, X-ray act to amper the Fox multiplier. So probably would be an interesting observational test to see if the occurrence of UFO or like accretion disk winds in general is more abundant in the X-ray weak population. It's not, I don't know if from a statistical point of view, there are that many sources that it is possible to do like a population study, but it could be interesting to see if effectively in a source there is a strange like reduction of X-ray flux. This should like help the wind to leave the system.
Yes, thank you very much. Two very nice points. So starting from the second one, we had a study published by Luca Zappacosta this year, where he exactly showed that. So he takes the most luminous in the optical, the most luminous quasar in the optical from the WISH sample, and then he studies it in the X-rays, and he can demonstrate that if indeed all the quasars that are X-ray weak, so they're not absorbed, they're not weak because they're absorbed, they're really weak, have the most powerful wind in the optical UV. So this is what we can say at the moment. We cannot say anything for the UFOs because so far we don't have statistics, not individual objects, not in big samples to answer the same question. And that's also the reason why my work with Daniel Proga is focused on UV absorbing features. So when we speak about very strong, very powerful wind, we speak about UV absorbing winds because the X-ray very powerful. We really don't have a clear idea of how to fit them in this scenario. And then this connects to the first point that you made. And I would like to connect with the very last result that I showed. I really had no time, but I was amazed by the result by Claudio Ricci and collaborators. So that's a case of an AGN, for example, which was like a standard AGN with an accretion disk and X-ray corona. But then suddenly, because of the interaction with a star, probably, but suddenly it lost the gas. It lost the inner portion of the disk, and it lost eventually also the X-ray corona. So that is a case where we were able to observe live the disappearance of the gas that could fuel the AGN. And so this made us think that yes, the picture that we made was way too simplistic. I mean, we knew that it was simple, but reality is much more complicated. So yes, in the future we should absolutely take into account the variability of the intrinsic flux of the source and how this does reflect on the characteristics of the wind. And I think there would be nice surprises. That's my guess. So thanks a lot for the two comments.
Okay, thank you to you.
It's from Fabio Fontanotte for Francesco. Please, Fabio.
Hi, can you hear me?
Yes. Hi.
Okay, thanks. Hi, Francesco. Nice talk. So I would like to connect with something that we discussed yesterday. It's about the radiative efficiency. So yesterday there was some suggestion that the radiative efficiency could vary according to black hole mass, luminosity, and redshift as well. So I was wondering if you ever tried to include such a variation in your models, and what's your take on this issue? Okay, can you, well, in your opinion, is that possible to constrain the relative efficiency in the same way as you did with the other variable that you showed?
So thank you for the question, Fabio. So yes, so I've done a lot of work on the continuity. So one of the best ways to constrain radiative efficiency is, of course, by using AGN population synthesis models, in the sense the continuity equation models. And the reason being that with using continuity equation models, you are really limiting the number of input parameters, so you have a bit more of flexibility and freedom and transparency there. So we have so in my can I share the screen? Am I allowed to share the screen once again? I just would like to show one plot on this, which so if you look, I don't know if you're able to see my screen right now. You see it?
See, yes.
Okay. So this is a very simple continuity equation model that takes into account the mean accretion rate of black holes, and this term over here contains the radiative efficiency. And in this case, I'm showing you the result of two models. The long dashed line is a model that that does not include dry mergers of black holes. And the solid line is a model which includes dry mergers in some ways in which we are inspired by what's suggested by the Fakuri-Ma merger rate of dark matter halos transformed into black holes using a certain M black hole and halo correlation. And to answer Fabio's question over here, you can see that if you assume that there are many mergers, I mean, not many, but if you assume that all halo mergers, tend to produce at some level some black hole mergers, you tend to overproduce the massive end of the black hole mass function quite a bit. And so one way one way in which you can get away by including many mergers and reconcile with the high mass end of the black hole mass function could be to increase the radiative efficiency with black hole mass, for example. We don't expect the radiative efficiency to change too much with redshift. We tried that in some of the models, but we failed. It doesn't give us the right answer. If anything, there is an increase with redshift, but otherwise we don't see any reason for varying too much the radiative efficiency with redshift. But if there is a dependence with black hole mass, this type of models should be able to show you this. On top of this, there are of course some direct measurements of, well, not measurements, but some more independent ways in which you can probe the radiative efficiency by using SED fitting of AGN spectra, and this has been done by several groups. So I'm not going to spend too much time on that, but there are papers, and if you want, I can give you the references. And those papers, basically, the result is that it's not easy to pin down the trends. Not even there, even though there are some groups that claim that there is some dependence, but it's not that strong with black hole mass.
If there are no other questions, I think that we can end here and thank again the speakers for the excellent presentations. And so it is 4:15, so we can declare this tourney and with no winners, of course.
Okay, thanks to everybody for being here. So we reconvene tomorrow at 3 p.m. as usual. The knights tomorrow will be Alessandra De Rosa and Alberto Cesana, and the chair Monica Colpi. So thanks to everybody, and thanks to Francesco and Margherita and Paolo, of course. And today also we had much more than 100 people. So thanks again, and see you tomorrow.
Okay, bye-bye. Thanks.
Thank you, bye.
Ciao.
Bye, thank you. Ciao.
Thank you.